Hello. Now we will calculate the capacitance for a parallel plate capacitor. Now, as the name suggests, in this capacitor will be having two parallel plates. So this is plate 1 and this is plate 2. So we are having two parallel plates, and the cross-section area of the plates is capital A and the distance between the plate is D. That one thing, the dimension of D is very small compared to the dimensions of A. So basically this distance is very small compared to the width and the length of these plates. So they are very nearby. These plates are very nearby. So that if any point inside, if you with respect to this point, if you see the plates, they will look like they are of infinite dimension. So they are very nearby plates. So only for understanding purpose, I have made this a little bit far away. But when we go for the parallel plate capacitor, the distance between the plate is very small. Okay. So we want to calculate the capacitance for this. As we already know, to calculate the capacitance, we have to place the charges. Since we see two objects here, separate objects. So one object I'll give plus Q charge and the other object I'll give minus Q charge. So net charge remains 0. Again, due to symmetricity, we can say the charge will be uniformly distributed onto these plates. Okay. So plus Q charge will distribute it uniformly over to this plate and the minus Q charge will uniformly distribute it onto the other plate. Okay. The charge density, surface charge density for either plate can be defined as Q by A. This is the surface charge density. So charge density onto this plate as well as this plate is Q by A. A is the cross-section area. Okay. Now, to calculate capacitance, we have to calculate this potential. See, in this whole structure and the nearby, this is having the maximum negative charge and this plate is having maximum positive charge. So this plate, nearby to this plate, the potential will be maximum, and nearby to this plate, potential will be minimum. And we defined V as V max minus V minimum. So we have to calculate the difference between these two potentials. Okay. So let's go for general point in between the plates. And at this general point, let's calculate the electric field. This plate is 1 and this plate I'm calling 2. So at this general point, if I want to calculate the electric field because of this plate, this is a positive charge. And due to the positive charge, the direction of field is away from the charge. So it will be in this direction. So E1 will be towards right. Now I'll define the field due to the second plate. Since second plate is having negative charge, the field due to negative charge will be towards the charge. So it will be in the same direction. So you can see both of these plates, the field due to both of these plates are in the same direction. Okay. And as we already know, the E1 magnitude wise, the E1 and E2 both will be same and the formula will be sigma upon 2 epsilon naught. Because see, the distance is very small. Distance of this point with respect to the plate is very small. So these plates, they behave like infinite dimension plate. And just to check, I want to calculate the field outside this plate as well. So if at this point, if I want to define the field, due to the positive charge, the field will be away from the positive charge. And due to this negative charge, the field will be towards the negative charge, E2. I'm calling it dash. Because obviously magnitude will differ a little bit. Similarly, onto this side, field due to 1 will be away from the positive charge, E1 double dash I'm calling, and the field due to this negative charge will be towards the negative charge. Now as you can see, the distance wise, the magnitude of E1 dash and E2 dash will not be same because the distance varies. But the thing is, this D is very small. So the variation in distance will not be that much. And because of that, we can safely say that E1 dash is approximately equals to E2 dash. Similarly, E1 double dash is approximately equals to E2 double dash. So because of this reason, electric field will be 0 onto this side as well as onto this side. There will be only electric field between these two plates. This is also a very good example where the field is confined within the plate. So an electric field, the energy basically it's not going outward, it's only within this. Okay. So this is same. So let's calculate the net field at the general point. This is inside point P. That will be E1 plus E2 because both the fields are in the same direction. So that will become sigma upon epsilon naught. And as you can see, let's put the value of sigma as well. That is Q upon A epsilon naught. Now you can see this electric field inside this region, it is constant because the Q is constant, A is also constant, and epsilon naught is also constant. So between these two plates, electric field is coming as a constant field. And when the electric field is constant, in that case we have a relationship between the electric field and the potential difference. The potential difference delta V upon delta X is defined as E. This is the formula, but this formula is valid when E is constant. So if I'm having 2 points A and B, and the distance between these 2 points is delta X, then VA minus VB upon delta X is defined as E, which is the field between these 2 points. If E is constant, that's the formula I'm using. So this formula I can apply between plate 1 as well as plate 2. So here the higher potential, here the lower potential. So V1 minus V2 divided by distance between these two plates, which is D, will be equals to, so potential difference between the plates divided by distance between the plate will be equals to electric field between the plate if electric field is constant, which is in this case. So let's put the value V1 minus V2 will be equals to Q upon A epsilon naught, here it is D. And this V1 minus V2 is nothing but V max minus V minimum, which we can replace as V, and that will be equals to Q D upon A epsilon naught. Or we can say it will become Q by V is equals to A epsilon naught upon D. So this is the result we are getting. Now let's compare this result. Compare this with standard equation of capacitance, which is C is equals to Q by V. So upon comparison, we will get C as A epsilon naught upon T. So this is the formula for capacitance in case of parallel plate capacitor. Okay, this is our parallel plate capacitor, and this is the formula we are getting. As you can understand, outside the parallel plate capacitor, the field is zero. So there is no potential change happening on this region as well as this region. So whatever potential is at this point, it's similar to till infinity. Whatever potential is there till this point, it is similar till infinity. So whatever potential difference is changing, it is changing between these 2 points, and that's the potential difference we have calculated. With the use of electric field within this region, which comes out to be constant, so we don't have to go for integration, we can directly use the formula. Okay, so this is the capacitance we get. Let's discuss this result a little bit more. In this case, if you see the A, so if you remember, this is the condition we defined. Dimension of D is very, very small compared to A. So if A upon D is very, very, very large, or we can say the D upon A is very, very, very small. Both are same things basically. So if dimension of A is large, very large compared to D, then A by D will be very large. And if A by D is very large, in that case, this result will lead towards C being very large. So if you want the large capacitance, in that case, these plates should be very, very nearby to each other. Or we can say the ratio of D upon A should be very small. So the cross-section area, the dimensions of the cross-section area should be very large compared to the distance between the plate. So if the dimensions are in the meter, dimension of the cross-section area are in the meter, this distance should be in millimeter. If the dimension of cross-section area are in millimeter, the distance should be in mu meters. Okay, so that's how we go, because we want more capacitance. So it's not dimension, individual dimensions which are important. It's the ratio which is important. The ratio of A upon D should be large, not the A and D individually. We want the ratio of A upon D should be large. If the ratio of A upon D is large, in that case, the capacitance for this capacitor will be large. Okay. So this is your capacitor, and this is the formula. One should memorize this formula because many times you want to use this formula directly. This is the capacitor in commercial uses, this is the capacitor we use because it's very easy to construct. At the same time, electric field is confined within the region. So the electric field due to these charges will not affect the other instruments which will be outside of this capacitor. So this is a commercial version of the capacitor. Parallel plate capacitor is a commercial version because I'm also a capacitor, but I'll not use myself. This is a commercial version. This is the capacitor which will be used in your electronic instruments. Okay, so thank you.